Hello friends, welcome back to another session on coordination compounds. In this session, we are going to check crystal field theory. This is our last part of coordination compounds. Now, whenever we are asked with crystal field theory, we have to draw a diagram. Which diagram do we have to draw, sir? I'll just come to that in a minute. But before that, let me just tell you that it's the splitting of d orbitals, and our d shell or d subshell or d sublevel is having a total of 5 different orbitals. Namely, the orbitals are dxy, dyz, and dxz. These are the different orbitals located between the different axes x, y, and z. Right? You know that this is x, y, and z. So these are the three orbitals. I mean, I told you there are total 5. So, but these three orbitals like dxy, dyz, dxz, these three orbitals lie in one geometry, one plane. What is moving outside the plane is dz square and dx square minus y square. These two are higher energy orbitals. They are moving out of the plane. Okay, and they are having a higher energy. Even if this does not make any sense to you, just relax. Okay, so just remember that whenever you have CFT coming in your exam, first thing is you draw this diagram. Okay, so basically we are going to split. These are the 5 orbitals. This is the average energy of d orbitals. What did I tell you? That the dx square minus y square and dz square, the last two orbitals, dx square minus y square and dz square, these are having a higher energy, and because they are having a higher energy, I've placed them over here. And the dxy, dyz, and dxz, they are having a lower energy and they are placed here. Whatever is having a lower energy is obviously more stable. I always give this example. If you are having a small child in your house, right, this small child will always be up to something. Maybe he'll pull your hair, he'll write on the walls, he will tear the pages of the notebook, he will do something or the other. He's always up to something. Why? Because this child is having a lot of energy meaning low stability. Okay, is very unstable. On the other end, if you are having an old man, right, old man can sit in one place, okay, watch television for 4 hours without moving. Why? Because he is having a lower energy, and when energy is low, stability is high. So this is your old man. It's having low energy and high stability. This is having high energy and lower stability. So now when I'm telling you that there is an energy difference between these two, so we call this as T2G. The energy of this, we call it as T2G. Okay, and here the energy we call it as EG. This is having a higher energy. I hope you are able to see that. Yeah, this we are calling it as EG, and this we are calling it as T2G. So when I write delta naught is the difference of energy. Like, what is delta? What is delta T? Delta T is change in temperature, T2 minus T1. We have seen that in thermodynamics, isn't it? We have seen that in chemical kinetics also. Okay, then what is delta pressure? The change in pressure. Change in pressure, P2 minus P1, final pressure minus initial pressure. So similarly, here we are going to have this delta naught. Delta naught will be Eg minus T2G. Okay, higher energy minus lower energy, Eg minus T2G. This is going to be our delta naught. Okay, so I hope you have understood. I'll just quickly brief through this once again. These are the 5 orbitals of the d sublevel. This orbitals of the d sublevel are dxy, dyz, dxz, the first 3, which are on the same platform, which are having the same energy, which are planar. The other 2 are out of the plane and they're having a higher energy, dx square minus y square and dz square, which are on the top. So the energy of this is labeled as Eg, the energy of this is labeled as T2G. Difference between these two energies is delta naught. This difference between two energies is called as crystal field splitting energy. So why do we need to study this? What help does this give us? Crystal field splitting. Crystal field splitting tells us about why there is a color change in a particular compound when the number of ligands change, or there is a change in number of unpaired electrons. So obviously the electrons, they are absorbing a different wavelength. If they change, they will absorb even more different wavelength and emit a different wavelength. That's why the color will change. Even if you have not understood, just hold on. We are going to go and dive deep. Yeah, the energy difference between two sets is called crystal field splitting in tetra field and abbreviated as delta T. So if there is a tetrahedral field, it's that delta naught for this is delta T whenever it is tetrahedral, and if it is an octahedral field or octahedral complex, it's called as delta naught or delta O. Delta T and delta. So the previous one was obviously octahedral, that's why it was called as delta O, and otherwise if it's a tetrahedral complex, then it will be called as delta T. If it is octahedral complex, then delta O. Just a second, what was that last point here? It has been found that delta T is roughly equivalent to 4 by 9 delta naught. So the energy, the difference in energies for a tetrahedral complex is equivalent to 4 by 9 of that of the octahedral difference of energies whenever it is an octahedral complex, right? So next, yeah, now there are two kinds of ligands, right? One are strong field ligands and the other one are weak field ligands. So let us see which are the strong field ligands and weak field ligands. Now you have to learn this table or this chart from I minus to Cn minus and Co. So the initial ones obviously are weak field ligands. I minus, Br minus, H2 minus, Cn minus, Cl minus, NO3 minus. These are considered to be weak field ligands. And the strong field ligands are towards the end: cyanide, carbonyl, NO2 minus, En, NH3, Py, till Py will consider. These are our strong field ligands, and the between ones will be medium field ligands. So we will consider this as weak field ligands, and these are strong field ligands. So strong field ligands have a greater splitting of the d orbitals. The energy difference is greater, and in weak field ligands, the energy splitting is comparatively smaller. So let us see what effect they exactly have. Okay, so the electronic configuration of complexes depend upon the crystal field splitting. I mean how much of energy they are, the differences there in the you can say dx square minus y square dz square, that is the high energy orbitals and the low energy orbitals. Now it depends upon whose electrons are there. अगर obviously d में electron कौन दे रहा है, d में electrons ligands दे रहे हैं, और ये ligand अगर strong field ligands है तो ये difference of energies ज्यादा होगा, right? अगर ये weak field ligands है तो difference of energies कम होगा. Okay, then in octahedral complexes, the 3 orbitals are of lower energy and 2 orbitals are of higher energy. That's what we saw for octahedral complex delta naught. And according to Hund's rule, electrons occupy a set of orbitals of the same energy one at a time with their spins. मतलब Hund's rule तो सबको पता है ना कि पहले like say for example Hund's rule अगर नहीं पता आपको 11th standard का है ना, पता तो है. तो अगर say for example इसमें electrons fill करने, 5 electrons fill करने, so do we fill like this 1 2 3 4 5? नो, हुंड बाबा आके मारेगा हमको, राइट? सो हुंड्स रूल क्या बोल रहा है? फर्स्ट फिल द इलेक्ट्रॉन्स विद द सिमिलर एनर्जीज इन द सिमिलर स्पिन ऑफ द same orbitals and then go for the opposite spin. That's what Hund's rule says, right? So d1 d2 d3, each electron can occupy a separate orbital in the lower set as shown below. So first we can fill the lower energy orbitals as d1 complex, then d2 complex with 2 electrons and d3 complex with 3 electrons. So we can call this as t2g1, t2g2, t2g3. Okay, then all the 4 electrons get occupied, the lower set of orbitals with electrons get paired in t2g4. It experiences a strong repulsion from the electron already there. Okay, the 3 electrons occupy a lower set of orbitals and the 4th electron goes to the higher set of orbitals T2G and EG1. What does that mean? It means I'll show you through a diagram if it's given over here, or else I'll draw the diagram. ठीक है, अगर say for example यहाँ पे, let me delete this, yeah. So if this is the lower set of energy orbitals and this one, so if you are filling electrons over here and if you want to four electrons, fill 4 electrons, then the 4th electron, if it is coming over here, then this electron will experience a repulsion from the other electrons. So if this electron is filled over here, then the repulsion which is being experienced will be less. Okay, that is what was meant by that particular point. Okay, we pressed the wrong HDMI. Yeah, yes. So now if here I told you the repulsion will be higher if it is filled like this, repulsion will be higher. 4th electron, if it is filled over here, repulsion is higher, delta naught is higher. And if the 4th electron is filled here, then the repulsion is smaller and the delta naught is small. So this is seen in the strong field ligands. The strong field ligands fill electrons like this, and the weak field ligands, they will fill electrons like this. So I told you that if there are strong field ligands, the energy difference is higher, and when there are weak field ligands, I told you that the energy difference is lower. Now, strong field ligands, already I told you, low spin complex and weak field ligands form high spin complex. Then which of the following is or are strong field ligands? So cyanide is a strong field ligand, and carbonyl is also a strong field ligand, whereas chloride and iodide were weak field ligands, isn't it? Now, which of the following is a weak field ligand? Just to check whether you are paying attention, the answer will be chloride and iodide. Yeah, I think you're not able to see this, right? Let's just move the camera down a little. Yeah, so chloride and iodide, these are the weak field ligands. So after answering those simple MCQs, now let us connect let us understand the application of the crystal field theory. Okay, so as we know that there are obviously 5 orbitals in the d subshell, as namely we have already discussed dxy, dyz, dxz, dx square minus y square and dz square. So we will be splitting this according to the crystal field theory. So when electrons from other atoms, that is from the ligands, ligands approach these 5d orbitals, the 5d orbitals split into two energy levels, as discussed dxy, dyz, dxz, and dx square minus y square and dz square. So I've told you why these are having high energy, they go up, and these are having low energy, that's why they're down. So now when an electron from an orbital, let that be from weak field ligand or from strong field ligand, okay, so when it is coming in, or when this ligand is lost, or when the ligand is entering, electrons of the ligand are entering into the d subshell, or electrons from the ligand are being lost. That means sometimes what is happening, like we had seen no in the example, कि ये किसका, ये डी जो डी सब लेवल है, ये डी सब लेवल किसका डी सब लेवल है? इट्स ऑब्वियसली ऑफ द सेंट्रल मेटल एटम. ओके, सेंट्रल मेटल एटम कोबाल्ट, जैसे कि थोड़ी देर पहले हम लोग ने वर्नर्स थियरी में, नॉट थोड़ी देर पहले, इन द प्रीवियस वीडियो, राइट, वर्नर्स थियरी में फर्स्ट वीडियो में देखा था CONH3 एंड Cl3 ऐसा है. तो जब NH3 चला जाता है, NH3 इज अ लिगैंड, जब तो चला जाएगा तो ऑब्वियसली उसके इलेक्ट्रॉन्स थोड़ी छोड़ के जाएगा, इलेक्ट्रॉन्स भी लेकर जाएगा. सो दैट इज द टाइम व्हेन द इलेक्ट्रॉन्स आर मूविंग आउट, and when the electrons are moving out, what is happening? The Cl is coming in. So ligand electrons from Cl will fill the d orbitals of cobalt, and when NH3 left, the electrons were moved out from the d orbitals of cobalt. So when these ligands are changing, now if I say for example I include a water molecule over here, I remove the Cl, send the Cl as counter ion, I introduce a water molecule over here, so the color will change. When Cl was inside, that will show a different color because there were electrons of Cl entering into the d sub level, d orbitals, then again the color will change. When there is water, the color will be different. When there is NH36 Cl3, then also the colors are different. I told you, I've seen that video. Okay, if you want, I'll drop the link, okay, of that video in the description box, or I'll pin it in the comment box. Okay, so there you will be able to see that CONH36 is having violet color, CONH35 is having green color, CONH34 is having a different color. So all those, when the moments NH3 is changing and Cl is coming inside, the electrons are changing, the electrons in the d orbitals are changing, and therefore the color of that compound was also changing. ओके अगर आपको चाहिए तो मैं इधर ही दिखा देता हूं वो पीपीटी खोल के, क्योंकि आप आलसी लोग हो, ठीक है, आप वो वीडियो पे क्लिक करके देखोगे या नहीं देखोगे पता नहीं, बट पहले इसको कंप्लीट कर लेते हैं, एंड फिर अगर इफ यू वांट आई विल शो इट टू यू. ओके, तो अब देखो ये एक नया इलेक्ट्रॉन यहां पर आ गया, ठीक है. अब नया इलेक्ट्रॉन यहां पर आने के बाद में क्या हो रहा है? इट इज सेंडिंग इन लाइट, राइट, ये लाइट यहां पे सेंड कर रहा है, मतलब ऑब्जॉर्ब कर रहा है, राइट. तो दिस इलेक्ट्रॉन इज अब्सॉर्बिंग द लाइट फ्रॉम द सोर्स ऑफ लाइट, and when it absorbs light, it will get excited. Have a look. When it absorbs light, it gains energy, it gets excited, and when it gets excited, it will not stay here for its lifetime. It will lose energy. The amount of energy which it had absorbed, that same amount of energy it will emit, and when it will emit the same amount of energy, what is going to happen? It is going to emit the form of energy in the form of light, and the color, the wavelength which it emits, that will be the color of this compound. Say for example, ये blue color का है यहाँ पे, राइट, ब्लू कलर का इसके लिए है क्योंकि वो एक पर्टिकुलर वेवलेंथ को क्या कर रहा है, यहाँ पे विजिबल लाइट व्हाइट लाइट है, तो वेवलेंथ ऑफ लाइट को ऑब्जॉर्ब कर रहा है, और ऑब्जॉर्व करने के बाद में इसके इलेक्ट्रॉन्स एक्साइट हो रहे हैं और जब नीचे आ रहे हैं, नीचे वापस आ रहे हैं, तो दे आर एमिटिंग सम वेवलेंथ. दैट वेवलेंथ विच इज बीइंग एमिटेड इज द कलर विच वी सी. सो दिस इज कॉल्ड एज डी डी ट्रांजिशन. क्या कहते हैं इसको? डी डी ट्रांजिशन. ओके अगर पीपी में हो रहा है तो इट्स पीपी ट्रांजिशन, इट्स डी एन डी ऑर्बिटल में हो रहा है तो इट्स डी डी ट्रांजिशन. एज वी ऑल नो, हायर द एनर्जी लोअर इज द स्टेबिलिटी. जितनी एनर्जी हाई उतनी स्टेबिलिटी कम. तो स्टेबल होने के लिए इट विल लूज एनर्जी एंड इट विल अगेन फॉल बैक. सो नाउ इट इज लूजिंग एनर्जी. while losing energy it is emitting a wavelength of light which is seen by our eyes. ओके और ये एनर्जी लूज करके, वेवलेंथ ऑफ लाइट लूज करके, एनर्जी लूज कर रहा है, उसकी पर्टिकुलर वेवलेंथ है, वो लूज एनर्जी लूज करने के बाद में फिर से कहां पर आ गया? ग्राउंड स्टेट में आ गया. एंड वी आर एबल टू सी अ पर्टिकुलर कलर ऑफ दैट. ओके जो जो वेवलेंथ ये यहाँ पे एमिट कर रहा था, तो से फॉर एग्जाम्पल अगर रेड कलर की वेवलेंथ एमिट करेगा तो ये रेड कलर का दिखाई देगा. अगर ब्लू कलर की वेवलेंथ एमिट करेगा तो ब्लू कलर का दिखाई देगा. अगर ग्रीन कलर की वेवलेंथ एमिट करेगा तो ग्रीन, मतलब 400 नैनोमीटर के आसपास है तो वायलेट इंडिगो ब्लू दिखाई देगा. और अगर 800 के आसपास है तो ऑब्वियसली रेड दिखाई देगा. एंड बीच में कहीं पे है लाइक 600 के आसपास है तो ग्रीन दिखाई देगा. Okay, so that's how these elements are able to show different colors. Okay, now I had to show you that क्या कहते हैं उसको. तो मैंने बोला आपको कि आप लोग आलसी हो, आप लोग पीपीटी खोल के देखोगे या नहीं पता नहीं, तो मैं आपके लिए पीपीटी खोल के दिखा रहा हूं अभी. राइट जो अब अगर NH3 6 टाइम्स है, ओके NH3 के इलेक्ट्रॉन्स है डी ऑर्बिटल्स में, तो कलर क्या है? येलो. NH3 5 टाइम्स हो गया, एक Cl अंदर आ गया, Cl के इलेक्ट्रॉन्स डी ऑर्बिटल में आ गए, पर्पल. राइट दो Cl अंदर आ गए, दो Cl के इलेक्ट्रॉन्स अभी डी ऑर्बिटल को एंटर कर रहे थे. दे आर ऑब्जॉर्बिंग अ डिफरेंट वेवलेंथ, एमिटिंग अ डिफरेंट वेवलेंथ. दैट वेवलेंथ इज ऑफ ग्रीन कलर. वेवलेंथ 600 के आसपास है, ग्रीन कलर. NH3 4 टाइम्स है एंड ये इसका ट्रांस का सिस आइसोमर बन गया. अगेन सिस आइसोमर में अगेन द इलेक्ट्रॉन्स आर स्वैपिंग, चेंजिंग देयर पोजीशंस. क्या कलर बन गया? वायलेट. अच्छा एक और चीज आपको बताना चाहूंगा, दैट इज अबाउट ये वाले कुछ इंपॉर्टेंट कंपाउंड. देखो जरा, Mn2 प्लस, जब Mn2 इलेक्ट्रॉन्स लूज कर रहा है, क्या भाई कलर क्या है? ऑरेंज. Mn6 वही Mn6 इलेक्ट्रॉन्स लूज कर रहा है, कलर क्या है? ग्रीन. वही Mn7 इलेक्ट्रॉन्स लूज कर रहा है, क्या कलर है? पर्पल. सो जब उसके इलेक्ट्रॉन्स चेंज हो रहे हैं डी ऑर्बिटल्स में, तो उसके इलेक्ट्रॉन चेंज होने पर वो एक डिफरेंट इलेक्ट्रॉन्स जो चले गए या आ गए, तो वो एक डिफरेंट वेवलेंथ अब्सॉर्ब कर रहे हैं, एक डिफरेंट वेवलेंथ एमिट कर रहे हैं. वेवलेंथ अब्सॉर्ब कर रहे, कहा है डीडी ट्रांजिशन हो रहा है, थोड़ी देर पहले दिखाया ना, डीडी ट्रांजिशन हो रहा है. इलेक्ट्रॉन कहां से जा रहा है? फ्रॉम ग्राउंड स्टेट टू एक्साइटेड स्टेट, डीडी ट्रांजिशन. और फिर एक्साइटेड स्टेट से फिर से ग्राउंड स्टेट में आ रहा है. जब ग्राउंड स्टेट में आ रहा है तो लाइट एनर्जी एमिट कर रहा है. तो जो लाइट एनर्जी एमिट करे, जो लाइट का वेवलेंथ एमिट करेगा, वो कलर दिखाएगा, चाहे ऑरेंज हो, चाहे ग्रीन हो, चाहे पर्पल हो. राइट यहाँ पे कुछ और डी ब्लॉक के एलिमेंट्स के एग्जांपल्स लाइक डीडी ट्रांजिशन जो दिखा रहा है, वेनेडियम है +5 है तो येलो कलर है. क्रोमेट का +6 है तो, बोलो ना, +6 है तो ऑरेंज कलर है, +3 है तो ग्रीन कलर है. राइट Mn का +7 है तो पर्पल, 6 है तो ग्रीन, 2 है तो ऑरेंज. Right, so I hope you have understood why crystal field theory is important and why it is helping us to explain the changing of colors in d block elements. सिर्फ d block elements हमको ये variety of colors दिखाते हैं. Thank you.